All right, we're going to take a look at using Gauss's law in a rectangular symmetry, or like we're finding the field that's created by a slab, like a charged slab. What's going on in this particular case is it says that the charge density is given by, it says minus 5y squared coulombs per meter cubed. So we kind of want to unpack what that means first. So the charge density is a function of the vertical position, and so what it's saying is if you're in the middle, I guess, of the slab, we'll call the middle dy equals 0. It's not charged, and then as you move out, it from the middle, it quadratically becomes more negatively charged. So it's got the most negative charge, like say on the very outer edges here. So I'll just kind of put a bunch of them in there. And then in between, it's just less so. But it grows quadratically as you go out, right? So it's just becoming more and more negatively charged. And then of course outside the plate, well, there's no charge. And so the way these things usually go is they say get the electric field everywhere, which the two different regimes are going to be inside the slab and outside the slab. And so we're going to want to use Gauss's law. And so usually what you want to do is, cut it up into those two regimes. And so let's start with just inside. And what you want to do is write down Gauss's law. The flux through any closed surface, that's what that means, equals Q enclosed over epsilon naught. Now of course this means the flux through any surface, and then of course with these Gauss's law problems, you tend to choose a surface for which this is easy to calculate, and the flux ends up usually collapsing down to EA perp, E times the area perpendicular to the field, because you choose a surface for which it's easy to calculate the flux. So what we'll do inside, again, what you want to do is you need to have some vision about what the field looks like. So this will be a super long rectangular slab, so we're kind of not worried about that dimension. And what's going to happen is the field, since this is negatively charged, right, the field's going to kind of be pointing inward everywhere. Right, it's going to, in general, the direction of the field is going to be like this. So it's good to have that sort of sense of what's happening first, because then what you can do is it helps give you some guidance for drawing your Gaussian surface. So magnitude of this thing is going to be changing in funny ways, but the direction's all inward. So what you're going to want to do is, or one strategy is to choose a surface for which it's easy to calculate the flux, and that in this case is just going to be I'll just draw it solid in blue here. It's going to have a rectangular symmetry, okay? So imagine this is going to be my Gaussian surface, and it's going to have this dimension here I'm going to call y. So from the midline of this thing up to the edge of it, and I want this to be flexible because I'm trying to find the field at different positions. So that dimension is going to be called y. And so what we want to do is get the flux through the thing. Well, other things that we ought to do is the top and bottom surface of this thing is going to have area A. I'll just call it A. You can't really see the in and out of the board dimension, but it would have some dimension back into the board too. But whatever it is, I'm just going to give it a area A. And then the height from the midline or whatever is called y, so I guess this thing is 2y wide, all right? And so what we're going to do is get the flux. Well, there's only going to be flux through the top and bottom of this thing. You have field punching in and punching in. So the field, or the flux is going to be the flux through the top and the bottom of this thing. Flux top and flux through the bottom equals Q enclosed over epsilon naught. Right. Well, the flux through the top, it's coming inward, so you'd say minus E times A for the top and minus E times A for the bottom. Right. So we don't know what the magnitude of the field is, but we do know that it should be uniform along the top of this thing and along the bottom, so long as this thing is a wide slab. So you have minus EA, well, plus another minus EA. So you basically get minus 2EA. All right? Equals. And then what we want to do, and this is usually where the labor comes in Gauss's law, is we have to figure out how the heck much charge is inside this thing. Right, so we're going to do a little side project to get the Q enclosed. I usually like to do the work for the Q enclosed like off to the side somewhere and then kind of put it back in. So let's work on that. Well, Q is going to be the sum of the little bits of charge. That's always the case. And then you need to figure out how to carve this guy up to get the little bits of charge that you want to add up. You could do like dx, dy, dz for a little volume of charge. But what you probably want to do here, or an easy way to do it, is instead of choosing a teeny tiny volume element, what you could do is choose a little volume element that looks like this. It'd basically be like a really thin rectangular slab. This would be like your little itty bitty volume. So right, your little bit of charge, it's going to be charge per volume times volume, or rho dV. Charge per volume times volume. And so what we would do if we choose this little slab here to be our mini volume, our dV, so let me just kind of make a line up here. Our little volume is going to be basically the area of that slab times its itty bitty thickness. So the area of that slab is A, and the itty bitty thickness would be dy. Right, so there's our dV, and so then what we can do is just kind of plug this in. So what we want to do is get the total charge inside this slab, and so we're going to want to go from, well, let's just plug in first. Rho is minus 5y squared, and the dV is going to be a dy. Right? And then what we want to do if we want to get the whole slab is we want to go from like minus y to y. You could also say 0 to y and double it. I'll just do it this way for the moment. Minus y to y. Right? And so let's get it, once we evaluate this integral, what that's going to be is the total charge inside of our Gaussian, they use the old-timey term when it's rectangular. It's a Gaussian surface and we're finding the total charge inside. I think the old-timey name for it when it's shaped like this, they call it a Gaussian pillbox, they call it. So let's quick get this. So that's going to be equal to, our Q enclosed is going to be, well, minus 5a is, these are constants. And then this y squared is going to integrate to y cubed over 3. But then evaluated at minus y and y equals, so really what, well, so you get minus 5a, and then, well, y cubed over 3, minus, and then you have to do minus y cubed, so it'll be like minus a minus, so you'll get plus y cubed over 3. So finally, in all its glory, you'll get the enclosed charge is going to be minus 5a y cubed over 3. So just to pause to see what the heck that's saying. That's saying that in this blue box, that the amount of charge you enclose actually depends on y. And in fact, it seems like it grows like, it's going to grow like y cubed. It's going to grow like the volume of, or it's going to grow as you increase the volume of this thing. So there's a y dependence on how much charge is enclosed, right? And so, well, now we've got the charge enclosed, so that's where you go back here and put it into Gauss's law. So you get minus 5a y cubed over 3, and then don't forget the epsilon naught. That's easy to keep out. Epsilon naught. Now this happens all the time. We're almost done actually now. This happens all the time in Gauss's law. When you use Gauss's law, the properties of your imaginary surface tend to cancel out because, right, the electric field at a certain point in space shouldn't depend on some imaginary surface that you thought of, right? Like it doesn't care about you. And so that part will cancel out. And now what we can do is we can just solve for the magnitude of the field. So the magnitude of the field, just divide that 2 over. So it looks like it's going to be the negative 2 over, I guess. It's going to be 5 over 6 dividing the 2 over, yeah, 5/6 y cubed over epsilon naught. Right? So the strength of the field grows like y cubed. Now what people will do, that's the magnitude of it, right? That's the magnitude. Now we already know from the sign of the charge that it's got to kind of point inward, right? The field only depends on the enclosed charge. So you have a bunch of negative charge in here. Field would point inward. So what you want to do to sort of make this a vector is what you do is you'd say it's a vector, and then you'd say like it points in the, say, the minus y hat direction if above y equals 0, and it points in the y hat direction if below y equals 0. Right, so there's your expression for the electric field. Right, so that's inside of the thing. Right, so what we can now do is shift to outside. Now the way these Gauss's law problems tend to go is oh, did I forget a 2? I did. I forgot a 2. Y cubed over 3 plus y cubed over 3. This should be a 10, and then this should be a 10. And so then what that makes this is 5/3. So I almost messed that up. So 5/3. So check that. Be careful. I did make a mistake there. Now it's fixed. 5/3 y cubed over epsilon naught. Now what we're going to do is get the field outside this thing. Okay. And so when you do these problems, you don't want to redo a bunch of like unnecessary work. So when you go outside, the only thing that's going to change is your Gaussian surface. You're going to make like this now, because you're going to be kind of probing outside, right? The only thing that's really going to change is your limits of integration on the enclosed charge, because once you're outside, the flux through this thing is still going to be minus 2EA, because you get flux through the top and flux through the bottom. So this will stay the same when you're outside. This is all the same, right? When you're inside, though, all you change, or when you're outside, all that changes, you don't want to integrate all the way out to where your Gaussian surface is. You just want to go to the edges of the slab. So what you want to do here for outside, I guess I'll just do this in blue instead of rewriting everything, is you'll integrate from minus W over 2, which would be like the half the width of this thing. You're going to integrate from there, to W over 2. Right? So these limits would just change from y to W over 2 and minus W over 2. So all that's going to do is everywhere you see like the y here, it's going to be, you're going to put a W over 2 in there. So just substitute that in for the y. And what that's going to do is put a W over 2 in here. So that's going to make this guy W cubed over 2 cubed, which would be 8. Right, so that's just going to modify that a little bit. And what that's going to do is give you your enclosed charge, which is you're going to see is a constant now, right? So it's going to be minus, what's this, 10 over 24 is 5 over 12, a w cubed, right? Minus 5/12 a w cubed. And so that is your, that's your enclosed charge. And so then what you want to do is put that in for the enclosed charge here. So again, I'm just gonna write that in blue so we don't have to redo all this work. This would be, instead, I'm gonna put this in parentheses, it's gonna be minus 5aw cubed over 12. And so now when you get the field outside, so you don't want to redo, you don't have to redo all the work. What's changed here is now the amount of charge enclosed doesn't depend on how big your surface is once you're outside, because you've already got all of it. So this effectively is a constant. This ends up being a constant. Oh, I forgot the epsilon naught. Right? And so now what you'll do is you'll divide, again the a's cancel, just like before. And what you'll do is you'll divide the 2 under, the negative 2 underneath this thing. So outside, you can see if you just divide this guy by -2, the E outside is going to be 5/24 W cubed over epsilon naught. Right? Now, oddly, and then it's going to point also in these same directions, but that's your magnitude of it. It's also going to point inward. All right. So this is your field, your magnitude of your field outside, and it's also going to have these same directions. Now, what's odd about this, and you'll see this all the time with these like super long or infinite slabs, is that you notice the field actually has lost any y dependence. What it's saying is that it's a very constant field when you're outside of the slab, right? So you'll see that all the time. That may seem a little bit odd, like, wait, how can it be that the field doesn't get weaker when you move far away? Forgive a little hand-wavy argument, but like one reason is that, so when you're close to the slab, when you're here, right? When you're very close, you have a bunch of negative charge here, which of course is going to attract you down. You're going to have all this negative charge out here and all this negative charge out here that's attracting this way and attracting that way. And of course, that's going to cancel out. These horizontal components will cancel out. So when you look at what's going on here, the majority of the contributions to the field are coming from this charge that's pretty close to where you are, directly underneath you. Well, as you move up, the fact that you're farther away should tend to make the field go down, the field strength go down. But what kind of happens is as you move farther away, there's sort of more charge, if you want, within your like field of view that's attracting you down. And so that, I know that's a very hand-wavy argument, but that's a justification for how can it be that the field's so uniform outside of a large uniform slab. All right, so hopefully that helped. That's kind of how you handle rectangular symmetry with Gauss's law.